Question 4 begins with an empirical formula question. So best way to do those is by this table method that you learnt last term. So you take your three elements, put across the top, you copy down either the actual mass of the elements, or in this case the percentage mass of the elements, it doesn't matter. So we got 37.8 for carbon, 6.3 for hydrogen, and 55.9 for chlorine. And then what you want to do is to turn them from relative masses, which is what these are, into relative moles. And so you do that like you always do by dividing by relative atomic mass. So you divide by 12 for carbon, 1 for hydrogen, and so on. And that gives you 3.15 and 6.3 and 1.575. And these are now in the correct ratio in terms of moles, and therefore they're in the correct ratio to give you the formula, but they need to be whole numbers, and you generate those by dividing by the smallest of them. So you divide each of them by that one, which is the smallest, and that gives you 2 and 4 and 1. So that tells you that the empirical formula is C2H4Cl. However, that's not necessarily the molecular formula. Remember, that just means however many carbons you've got, there are twice as many hydrogens but half as many chlorines. That's what the empirical formula means. To turn that into the molecular formula, which it wants in part B, we have to take account of the MR. So what you do is you work out the calculated MR from the empirical formula, first of all, and compare that with the true MR. So the calculated MR from the empirical formula is 63.5, if you just add that lot up. But the true MR, it tells us in the question, is 127. Strictly speaking, what it tells us in the question is the molar mass is 127 grams per mole. But remember, the molar mass is numerically the same as the MR. It's just that MR doesn't have units, but it's the same number. So we therefore know that the true MR is 127. And we just find the ratio. So we just say 127 over 63.5 is 2. In other words, there are 2 lots of the empirical formula needed to give you the true MR. So that means that there are 2 lots of C2H4Cl in the molecular formula. Which means that it's C4H8Cl2. Okay, so that's fairly straightforward. You just need some evidence when you do questions like that that you haven't guessed, and therefore just sort of showing that you divide the true MR by the calculated one, or make some comment to this effect. But this idea of the factor of 2's got to be there in your explanation. Okay, so this is the molecular formula of H, and it tells us that if we hydrolyze this with hot aqueous alkali, we get butane 1,3-diol, and from that we can figure out what the structure of this compound is. So the first job, which is part 1 of question C, is to write down the structure of butane 1,3-diol. So butane, well, but means 4 carbons, an means it's saturated, so there's no carbon-carbon double bonds in there, and ol, remember, means that there's an OH group. So 1,3-diol means you have an OH attached there and an OH attached there. And we mentioned earlier, but I'll just say it again, just keep reiterating this, when you put OHs on, be very careful, make sure the bond connects from the carbon to the oxygen, not just vaguely somewhere in the middle, or worst of all to the hydrogen, because it's got to be clear that you know that it's the oxygen that's the one that's attached. So that's the structure for butane 1,3-diol. And therefore you can deduce that what H is just has the same structure, but it just has chlorines where the OHs were, because of course it's just a substitution reaction. The hydrolysis, wherever the OHs appear, that's where the chlorine was, and it simply got substituted. So it's very easy to figure out that that is what compound H was. Question 5 begins by asking us what ozone is, so you have to know that ozone is O3. Okay, so it's a form of oxygen, but instead of just forming O2, which is what you're most familiar with, you get 3 oxygen atoms in the molecule. So ozone is O3, and the reason it's important is because it absorbs UV in the upper atmosphere. So all that UV arriving from the sun, of which there's a great deal, most of it gets absorbed by the ozone in the upper atmosphere. And that's important because UV is tremendously damaging to DNA. So if all that UV made it down to the Earth's surface, it would cause a tremendous amount of DNA damage to us and to all the other living things. And if the DNA gets damaged, the genetic code is compromised, so you don't have stable life forms, essentially, in that case. And certainly in the short term, what it would tend to mean is that we would get a lot of cancers, particularly things like skin cancers. So it's important to avoid DNA damage due to UV. And the reason that's important is that it would help us avoid skin cancers. Okay, so that's why we care about ozone. In part B, it asks us to suggest a dot and cross diagram for ozone. Now you might at first think, oh well, it's easy to put 3 oxygens together because you could do that. I won't draw the dot and cross out for that, but you can see how that would work because each oxygen's forming 2 bonds like it normally does. But you can see that the bond angle in that's an equilateral triangle, so the bond angle would be 60 degrees. First of all, that's not what it says in the question, so that structure doesn't seem to be right. But you can also see that that's likely to be unfavourable because that's a very acute angle. Each of those oxygens has 2 lone pairs and 2 bonded pairs, so you would expect it to be like in water, a bond angle of about 104.5 degrees, classic non-linear angle, and it closed down massively from that. So you can see that if another structure is possible, it's likely to be more favourable. So if you thought that, yes, it works, but it doesn't fit the data in the question. So we've got to come up with something that would explain an angle of 120 degrees. So the thing to do is to put the 3 oxygens in a row rather than in a triangle. And the simplest way to see this is to start out by just drawing normal oxygen, O2, drawing the electrons in that, and then think about how we can stick the 3rd one on. So that's what we're going to come up with, but let's just do it a step at a time. So let's start with that and just remember how O2 works. So oxygen's in group 6, has 6 electrons in the outer shell. That means it can bring 2 more in. So we're going to expect to have 2 shared pairs, which we draw in the intersection there. And because oxygen's in group 6 and you've only used 2 from each one, that gives you 2 lone pairs for each of those. So how are we going to bring the 3rd oxygen in? We can't do the same thing again, because if we did, well, let's just try it. Let's just see what would happen if we brought the 3rd oxygen in and did the same thing again. So this oxygen would have 2 lone pairs, just like the one on the outside. The one in the middle would have used 4 out of its 6, so it would have 1 lone pair as well to account for all 6 of its original electrons. And that looks fine until you add up the total number of electrons around this middle oxygen, and then you realise it's 4 plus 4 plus 2 is 10. And because oxygen is in period 2, it cannot have more than 8 in the outer shell. When you get below period 2, it's possible to have more than 8. So then that would have looked okay. But period 2 elements, they just never go above 8. So that can't be right. So how can you get around that? Well, the way to do that is to remember that wherever you have a double bond, you could in principle just have a dative covalent bond instead. So what we could do is say, right, this end oxygen isn't going to share any of its own electrons, it's just going to accept sharing a pair that comes from the middle one, and that would mean that this oxygen actually has 3 lone pairs. Okay, so 3 lone pairs because it has all of its original electrons, but it's now sharing this pair from here, and that has the advantage that you now have 4 plus 2 plus 2, so only 8 electrons around the middle one. So that one is the structure that we want. So in other words, if you drew that out as a displayed formula, it would look like this. And does that fit with a bond angle of close to 120 degrees? Well, yeah, because that oxygen has 1 double bond, 1 other bonded pair, and 1 lone pair. In other words, 3 regions of electron density, and always what you write, remember, is that they are repelling each other. In its outer shell. Okay, and when you get 3 regions of electron density repelling each other, it's like trigonal planar, except that in trigonal planar they're all bonded pairs, so we can't call it trigonal planar, but you can see it's the same sort of angle. So the angle is close to 120 degrees. You would expect it to be slightly less than 120 degrees, because the lone pair repels more than the bonded pairs. But we're not going to worry too much about that. The main thing is seeing that that fits with the stated angle. Okay, so now we get in part C onto the mechanism by which CFCs cause ozone destruction. So this is an example of a CFC. So it's a chlorofluorocarbon is what CFC is short for. And the question asks us how it is that this can yield chlorine radicals in the upper atmosphere. So the reaction is just this. So one of these chlorines breaks off and we get that plus Cl dot. Okay, so we're just breaking the carbon to chlorine bond homolytically to make this radical and a chlorine radical. And the reason that happens in the upper atmosphere is because there's lots of UV up there, and the UV does it. So it asks us to explain it. So that may be enough, but it's better to spell it out and say that UV provides the energy to break a CCl bond. Okay, because it's all about just spelling it out to make sure that the examiner knows that yes, you understand what's going on here. And then it asks what kind of bond breaking event that is, and we've already used that term. It's homolytic fission, which means, remember, that when the bond breaks, one of the participating atoms gets 1 electron, the other gets the other. So the carbon gets 1, the chlorine gets the other. Okay, so then it wants a pair of equations to show how those chlorine atoms set about attacking the ozone. So this you really want to learn, because you can't very easily make this up. So remember from when we did radical substitution that what these radicals tend to do is to grab one atom out of the electron, out of the molecule that they crash into. And that's what this does. It grabs 1 oxygen out of the O3, so that leaves behind O2 and gives you ClO dot, which looks like that. What that has is still an unpaired electron here. So it's still a reactive species. So the ClO dot can now react with something else, And there's something else, and this is the bit that you really do have to remember because it's not very at all obvious, is an oxygen atom. And then again, you get a reaction where one atom is transferred, so you get O2 again and Cl dot. Okay, so in other words, this is an initiation event up here in part C, and these are propagation. So this is a propagation cycle, a chain reaction where each of these reactions produces the radical that feeds the other one. So we just need to break one molecule open like this, and we can go around this tens of thousands of times, producing lots and lots of ozone destruction just from a single CFC molecule being broken open. And that's why these CFCs were so damaging, that even though the amounts of stuff we produced were quite modest compared to the amounts of oxygen up there, it didn't matter, because one of these had the destructive power to destroy thousands and thousands of oxygen molecules. So that's what's going on there. You might think, why oxygen atoms? Isn't that a bit weird? We normally think of oxygen going around as O2 molecules, but remember, this is in the upper atmosphere. In the upper atmosphere, it's bathed in UV light because it hasn't been absorbed up there, and the UV can break open oxygen molecules to generate oxygen atoms. So that would be weird if we were saying that happened at the Earth's surface, but up in the upper atmosphere, that's fine. So that's the answer to part E. And then it sort of says, right, well, what's the overall effect of that? So you generate that just by literally adding the two equations together. So that means you add everything together on the left-hand side to get the overall left-hand side, everything together on the right-hand side to get the overall right-hand side. So if we do that, we get O3 plus O plus Cl dot plus ClO dot. And then on the right hand side we get 2O2 plus Cl dot plus ClO dot. And you can see that what's going to happen is that we have to do some cancelling, because Cl dot is on both sides, so it drops out, and ClO dot is also on both sides, so it too drops out. And so you get O3 plus O goes to 2O2. So that's the overall reaction, and it asks us to explain why we can therefore say that Cl dot is a catalyst. And the point is that it's not used up in the reaction, or rather it's used up but then regenerated, so overall the Cl dot is not used up in the reaction. It's necessary for the reaction because it plays a role in this key step to get the propagation cycle going, but it's then regenerated, so overall it's not used up and therefore it's a catalyst. That's the important thing. And part G just makes the point that this reaction sequence, which is how chlorine radicals destroy ozone, you can get the same kind of reaction sequence with other radicals because they can all generate the same kind of propagation sequence. And one that's very important is NO, which is nitrogen oxide produced naturally actually by the effect of lightning. So as it tears through the air, it can provide enough energy so that nitrogen and oxygen in the air can react. So this is naturally part of atmospheric chemistry, but it's also produced by aircraft engines. And again, it's the intense heat in the aircraft engine which allows nitrogen and oxygen in the air to react. And so the amount of this in the upper atmosphere is much higher, or significantly higher than it used to be, because of the effect of aircraft engines. And the thing about NO, if we just do a quick dot and cross diagram, again you don't have to do this in the question, but this is just a bit of background. If you think about how the dot and cross diagram works, oxygen's going to form two bonds like it always does, or usually does. So there it is, completing its 8 electrons by doing that. And if we look at where that leaves nitrogen, it's in group 5, it's used 2 of its 5, so it will have 3 left over. Okay, so it has an unpaired electron. So NO is actually a radical. And that's the key, because what Cl dot does, NO dot can do. And that's the way to memorize this, rather than think, oh, that's something else I've got to learn completely separately. Just think, I'll just modify this, because whatever Cl dot does, NO dot does. So here it grabs an oxygen out of there to and leaves O2 behind. And what will it become? Well, if it grabs one more oxygen, it'll become NO2 dot, which actually still has an unpaired electron. You can explore that with a dot and cross diagram if you want, or else just learn it. So NO2 dot is there, and because that's a radical, it can do what ClO dot did here and react with oxygen to produce O2 and to regenerate NO dot. Like that. So basically I've just modified this by sticking NO in wherever Cl was before, and by doing that you get exactly the same pattern. So when we generate the overall equation, add them together and cancel out, we get the same overall reaction. O3 plus O goes to 2O2.